This is Mrs. O'Neill for AP Chemistry, Chapter 20, Section 2, Part 1, Balancing Redox Equations or Balanced Redox Reactions. So your objective is going to learn how to balance these particular type of reactions or these equations using the method of half reactions. There are other kinds of methods that you might learn in college, but this is, to me, the most easy because you're doing the same thing over and over and over again. Again, it's following steps. First, however, pause the video, fill in the blanks, and then play to hear my words. Why they come up with redox for oxidation-reduction reactions, I don't know. Why they kind of swap those words, not sure, but it does, I guess, sound better, redox instead of dox-re. I don't know. So, first, we have to understand that a redox reaction means that you're changing oxidation numbers. So the first thing we're going to do is assign all the elements their oxidation or charge numbers. So for one of the elements, it's going to be oxidized, and for one of the elements, it's going to be reduced. So we have to pull out those half reactions in order to balance at the end. Remember that this is a transfer of electrons. It's a transfer between those two reactants. It's a transfer between two elements, and they are occurring at the same time. So we want to remember oxidation means lose electrons and reduction means gain electrons. That's going to help us understand where those electrons are going to go in our half reactions. So the half reactions is, again, two equations, two reactions that are going to make up the whole. They occur at the same time. So we have to decide or figure out which reactant or particular element is losing electrons and which reactant or particular element is gaining electrons. So let's look at this example. The first thing I want you to notice is it's already balanced. The reason I balanced the equation for you already is to understand the electrons, and we'll talk about that later. But normally you would have a regular equation, and you're going to use these half reactions in order to get to the balanced equation. So that's one thing to notice. Most of the time, your reaction is not balanced, and you're going to use these half reactions to balance. So the very first thing, assign all oxidation numbers. Why do we need to do that? Well, we need to understand, again, now in this case, there's only two elements. So is sodium being oxidized or sodium being reduced? And the same thing with chlorine. So let's assign all those oxidation numbers. You should be able to do that now from the previous videos. 0 to +1, since sodium is by itself, it gets a 0. It is now in a compound, so now it has that +1 charge. Chlorine went from a 0 to a -1. Again, very similar as to reason why. So what's going on here? Well, the lion went a grrr or box. You know me, I like the box. The bigger the charge, that's the guy that went into oxidation mode. So who's losing electrons is being oxidized. Whoever is gaining those electrons is being reduced. So whoever is becoming more positive, again, is being oxidized. Who's ever becoming more negative is being reduced. So sodium is being oxidized because it's getting bigger in charge. Chlorine is getting reduced because it's reducing in charge, right? Reducing or decreasing. So we also want to remember these other words. Remember that if we're being oxidized, that means we're the reducing agent, right? We're helping the other guy be reduced, and the guy that's being reduced is also called the oxidizing agent. Again, helps the other guy be oxidized. So let's look at these two reactants individually. So look at what's going on here. And again, the electrons, are the reason for it to be balanced is because of those electrons. So there are two Na atoms, and each of them is going to lose one electron, but there's two of them. So we need 2 electrons total. And the next slide, I'm going to get you to understand what's going on here for each side of the reaction. So oxidation again is occurring. If we look at the chlorine, now it's the opposite. Again, we have 2 chlorine atoms, the Cl2. It has to gain those 2 electrons in order to become 2 Cl minuses. So we need to really understand where those 2s are coming from and why we have 2 electrons. And again, that's going to be reduction. So oxidized, reduced, increase in charge, decrease in charge. Box. You know me, I always like the box. To me, whenever I think about the box, it's getting bigger in charge, oxidation. So now let's look at each side individually. And what do I mean by that? Again, so this is stuff we've already talked about. So let's look at this side as far as charge is concerned. There's absolutely no charge here. And if I take +1 plus 2 negatives, well, 2 positives and 2 negatives means neutral. So both sides of this reaction is neutral. Again, that's going to be really important later on when we start to really balance. So what's going on over here? Well, this side is -2 total on this side, and 2 times the -1 here is also -2. So on both sides is going to have a -2 charge. Again, this is going to be really important later, because one of the ways we're going to make sure we balance correctly is that our side on the left and our side on the right, as far as charge goes, is also going to be, it has to be equal to each other. Okay, so again, both neutral, good, both -2, good. So again, we're the reducing agent, and that's the oxidizing agent. Electron donor, sometimes it's also called that way, right? If it's an electron donor, it's giving away those electrons. So then obviously the guy that's being reduced is the electron acceptor, again, as a reactant. So electrons as the product side, again, here's our electrons as the product because it's being donated, is going to be our oxidation side. And so obviously if the electrons are the reactants, on the reactant side, it's being reduced. So many different ways of looking at it, and you need to kind of understand all different ways depending on how they're giving you the information or what information they want. So again, these two half reactions, one reactant's being oxidized, which means another reactant better be reduced. Otherwise, it's not a redox reaction. So all of the stuff we've said over and over again now. Metals tend to lose electrons, so that's one thing to look for. If you see metals and nonmetals, most likely your metal is going to be the guy that's being oxidized, and your nonmetal is going to be the one that's being reduced. However, with that being said, sometimes you'll have multiple metals in your reaction or multiple nonmetals in your reaction. So that means you got to choose which of the metals is going to be oxidized and which one's reduced. Same thing with the nonmetals. So most of the time you have one of each, but there are going to be plenty of times when you have just mostly metals or mostly nonmetals. So you'll have a metal that's going to be reduced. Doesn't feel right, but that's what happens. And we'll learn more about that too in electrochem when all we're dealing with is metals. So again, one metal is being oxidized and one metal is being reduced. So in a reaction, we need to write these half reactions. So here's example number 2. So again, here's a whole total reaction. It's a net ionic reaction because I'm giving you ions here. Notice again, sometimes they're giving you what state of matter it is. And notice that it's already balanced. This is not going to be the case for the next video when we truly have to balance the equation. But can we come up with who's being oxidized and who's being reduced? First thing is first, assign all those oxidation numbers. So did you get this, and did you get this? Hopefully you did. Knowing that information, is this what's going through your mind? Zinc is losing electrons, so that's the guy that's being oxidized, or it goes from 0 to +2. It's getting bigger in charge, so it is being oxidized, my box that I like to use. And again, reducing agent and electron donor. We can also think about hydrogen. Again, hydrogen is being reduced because it's going down in charge and all those other things that we talked about. So what are the two half reactions? Well, I always look at the oxidation first. Again, I just like to do things in order. So if I look at the oxidation reaction, I'm taking zinc. My electrons better be on the right side because I am donating those electrons. And if we notice the charge here, zinc 0 charge totally on this side, and +2 + 2 negative electrons on this side would be a total of 0 charge as well on the product side. For your reduction half reaction, again, I have my 2 H pluses plus 2 electrons, which should make sense because I'm going to accept those electrons. And this is a total of a 0 charge on the left side. And we also have 2 H's on the right, balancing the H's, and of course, 0 charge. So can you do, and I also wanted to explain this again, only gained one electron, right? Hydrogen technically only gains one electron at a time, but because there are two H's, it's actually gaining two total. We want to remember that the number of electrons with our half reactions are going to have to be equal. Very important when we get to balancing the reaction as a whole. So again, not only do the elements are going to be balanced like you're used to from Chem 1, but now the electrons are going to have to be balanced, and we'll see that. Notice as well, I'm always lining up my arrows. This again is going to be beneficial to you as you write your half reactions for oxidation and reduction. It's going to be real easy to understand how those, the product side versus the reactant side, and how we're going to eliminate them. So just as a quick thought too, notice in our overall reaction, we do not see any electrons because once we get our half reactions the way they're supposed to be, this 2 electrons on the left as a reactant is going to cancel out with the 2 electrons on the right. So again, I've already balanced them, so those 2 electrons would cancel out, but that's what we're going to get to. We're going to get to, okay, both electrons or both sides have to have the same amount of electrons in order for those electrons to cancel out, because you never see electrons in your overall reaction. All right, I would, if I were you, pause the video, see if you can come up with assigning all of the elements their oxidation numbers. Hint, 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 it's kind of already done for you because of it's a net ionic equation. And notice they're all metals, okay? It's not metal versus non-metal. So which metal is being oxidized, which one's being reduced? And can you come up with those half reactions, the electrons on the appropriate side and the arrows lined up? So step 1, which they're already there basically, so you didn't really have to rewrite them. But did you notice that zinc lost electrons, so he's being oxidized, and iron gained electrons, so he's being reduced? So the overall reactions, so there's our oxidation. So looking at the charge, +2 total on the left, +4 and 2 electrons, so +4 minus 2 would give me a +2 total on the right. Notice for redox, again, I lined up my arrows. Of course, there's the phone. Here we would have a +2 because we have a plus 6 total over here. We have a +6 total, and we have a plus, oh good lord, oh +6 plus the 2 electrons is a +4 overall, and here's a +4 as well overall. So we want to remember, again, that iron really gained those 2 electrons, but there are 2 of them. So we need those to be equal. And when we get there, again, both of these half reactions, we have 2 electrons on the left, 2 electrons on the right, and they will be canceled out. So next time, we will use these half reactions in order to balance a redox chemical reaction overall. See you in class. And wondering if you laughed as much as I did about that gosh darn phone ringing. But I refuse to make a new video.